So welcome to the hottest seminar. This week, we're very happy to have Jaz Myers, who will tell us about tangent bundles of spheres.
Thank you, Emily, and thanks to you and Dan and Chris, all the organizers. Carlo, I guess is. So I'm going to talk about a project that I've been working on with Ulrik Buchholtz, whose name is misspelled on the slide. I'm very sorry. Dan Christensen and Egbert Rijke on constructing the tangent bundles of spheres in homotopy type theory. And this horrendous image sitting before your eyes right now is actually an illustration of the Hairy Ball Theorem, where the idea that topologically a dog is basically a ball. You're wondering whether you can comb the hairs on this dog to lie flat everywhere, or whether there's going to be a cowlick. So we're going to cover that. So this is a talk in synthetic homotopy theory. And synthetic homotopy theory is essentially homotopy theory, like ordinary homotopy theory, the study of homotopy types and the properties of spaces that are invariant under homotopy. However, unlike classical homotopy theory, where we have homotopies are actually continuous deformations of continuous functions and other spatial objects, in homotopy type theory, we can do synthetic homotopy theory that just uses the universal properties of the various constructions involved. And I don't think it's too far of a leap to say that synthetic homotopy theory is, in a way, the homotopy theory you can do with the universal property of the pushout in the right environments. So this talk we're going to use Buchholtz. So that means we have these pair types, which I'm using this syntax for. They're sometimes called sigma types, and function types, which I'm using this syntax for, which are often known as pi types. And then all the usual features of Martin-Löf type theory with univalence. In addition, our main sort of higher inductive type, in fact, I think our only higher inductive type we're going to use here is the pushout. And then finally, we're going to use a bit of some higher level ideas in homotopy type theory, namely banded types, which Jarl talked about a little bit ago on this seminar. And cohomology. So my hope is that this is a quite elementary talk that if you've read through most of the hot book, you're ready to jump in and understand the whole thing. So I think it's fun there. So okay. So pushouts specialize to a number of important constructions in homotopy theory. Namely, we have the suspension is the pushout of the terminal maps over themselves. And so the suspension here is we have 2 points, north and south, and we sort of hang our space in between them as paths. So we have this universal way of turning our space into paths between 2 points. That's the suspension. The join is sort of similar. In fact, as we'll see on the next few slides or next slide, it's the same thing if you join with the right space. But the join is similar, except that you hang a whole space A by a whole nother space B. So you add all these paths between them like that. And the cofiber we're not going to use in this talk. I think I originally intended to talk a little bit about the cofiber in the Tom space, but it's not going to be here. But it's like it's in traditional topology, it's called the cone. So you just sort of cone off part of your space or the image of a function. And then the wedge we'll see a little bit at the end, and you just draw a new line between 2 points in 2 different spaces. So all of these are examples of pushouts, and we're just going to use a few of them here. In particular, we're going to use suspensions and joins. So the spheres are, in some sense, the simplest types you can write down, because they're just suspensions of the empty type. And so the zero sphere, we start at -1 with the spheres. The zero sphere is the suspension of the empty type, which is just 2 points north and south. And then when you suspend that, you get 2 points north and south with now 2 meridians between them, which are, you could call east and west, but they would be the meridional north and the meridional south, and so on. As you suspend up, you get all the spheres. Now, there's another way to form the same homotopy type. Through another inductive process given by iterated pushout, which is to start with the 2 element set -1, 1, or the zero sphere, if you will. Here I've written it as the 0 cube. and iteratively take joins. And so what this does is the difference between these two is that the suspensions, they don't have any points that we didn't put in any generating points on the actual equator. Whereas in the join version of this construction, we have the previous level sitting there as actual generated points on the equator. But with a not so difficult argument, you can show that the suspension of any type is the same as the join with a 2-element type, or the zero sphere, as I've written here, the zero cube. So these really do give you the same construction after all. So they're both the same, and we can use them interchangeably. And now, so that sort of choice ends up affecting the whole rest of our discussion here, because we're trying to define in this talk the tangent spheres of the tangent spheres of spheres, as I'll come to very shortly. So choosing what a sphere is does determine how we're going to do everything going on. So in this talk, I'm going to focus on using suspensions. Although how we actually ended up doing it, and how we sort of prefer to do it, is using joins and using the cube join. So I'm just going to keep that in mind here. Excuse me. So our goal in this talk will be to define the tangent bundles of the spheres and to do a little math with it. So here's the idea behind this. We have a sphere here, and for any point on the sphere, this is thinking classically, we can look really close to that point and find a little flat patch of ground there. And this is what's known as the tangent bundle in ordinary mathematics, right? If these were manifolds. Now, the problem with this point of view is that little patch of ground is contractible. It just contracts right back onto the point. So this doesn't tell us anything interesting, or what I should say is our target is to find this function that takes a point on the sphere and gives us this type, and that type will be the tangent bundle at that point. But if we were to use this normal picture where we just look at the patch around P, well, that would be a contractible type. It just contracts onto P. So that's obviously not interesting. So instead, what we're really going to define is the tangent sphere bundle. And I'll defend our use to drop the sphere in the terms tangent sphere bundle simply on the grounds that the tangent bundles already are always the same as the types that they are tangent to. So it only makes sense to look at the tangent sphere bundle. That's where all the topology happens. So what we can say is the tangent sphere of a point is the space of directions you could walk at if you started walking at that point. And so on the 2-sphere here, you have a 1-sphere or circle of directions you can move in on any point. And in fact, we can make an identification of that sphere, which, this sort of infinitesimal sphere that lives right around our point, with the actual great sphere that lives orthogonal to our point. So if you can look there, we sort of have this great sphere here, which is like an equator. If P were a pole, then TP would be the equator relative to that pole, right? So now that gives us some other important bit of information. By just drawing the picture like this, we've implicitly said, right, that the suspension of the tangent sphere, right, where we would hang it, suspend it by P and its antipode on the other side, which is not drawn yet, that suspension is just another way of talking about our original sphere, which was defined as the suspension through north and south, right? So we have this change of coordinates equivalence there, which we'll call theta P. And theta P is the equivalence that says P is going to be our new north pole, is the way to think about it. And what I really mean by that is theta P is an equivalence, and it sends north in the suspension of the tangent sphere of P to the point P in Sn. Okay. So this is it. This is the construction. It's right here. It fits on one slide. We're going to use that idea to put together this construction. So we're going to inductively define the tangent bundles of the spheres, and we're going to mutually inductively define it with this change of coordinates theta. So the case of n equals -1 is trivial. We're mapping out of an empty type, so that doesn't matter. All the juice is happening in this inductive step. So let's look at that. So Remember that the tangent sphere can be identified with this equatorial sphere relative to the pole that is the point we're at. So if we're trying to see what the tangent sphere looks like at north, it must be the original equator. So it's just Sn. If we're on n plus Sn plus 1, we start at north, the tangent sphere to north is Sn. If we look at south, then again, the orthogonal sphere is the equator. Now it's a little bit upside down, and we'll see that just in a moment, but it's still the equator, right? And so now, using the universal property of the pushout and univalence, so we have to define what we do as we move from north to south along a meridian. And that meridian is set at that point P, some point P on the equator. And so what are we going to do? We have to give an equivalence, or we have to give an identification, or generally an equivalence using univalence from Sn to Sn, right? And so now let's take a moment and think about what this does by looking at that little picture in the corner there. So if we fix a point P on the equator, right, then what we need to do is we're going to move north to south along the meridian determined by that point on the equator and watch as the equatorial sphere tilts over, right? If you visualize that in your head. And so we can now wonder what is happening. So obviously we start with the regular equator we started with, and we end with the regular equator we started with, but we flip over, right? And we flip over in a very precise way. And to see that, note that we flip over, we send P as we tilt over, gets tilted all the way around to the other side of the equator, right? But all the points that are orthogonal to P on that equator stay fixed, right? Those are defined in green. So the way to define this map, right, where we flip P to all the way to the other side, its antipode, and fix everything orthogonal, is first to take that equator, which is Sn, and rewrite it as the suspension of the tangent space of, it should, the sigma Tn sub P should be there, excuse me. The tangent space of P in the equator, which is those green dots in the picture, right? And then we flip. And flip here, I'll talk more about it on the next slide, but flip here is the function on a suspension that flips north and south. So remember that our theta was the coordinate change that sent P to the North Pole. And so when we flip, we send that North Pole to the South Pole, which will be the antipode of P. And then we change coordinates back to get back to the original equator. So that's the explanation of why we choose this map on the as the action of the meridian, of transporting over the meridian in this type family. Okay, so now this map clearly made use of theta, so now we have to go and define theta. So remember that theta is the change of coordinates that sends P to the North Pole, right? So if we are already at the North Pole, right, then there's nothing to do. So the North Pole, theta will send the North Pole to the identity equivalence on the suspension of Sn. Now, if we're at the South Pole, to think of what we're going to do, we are already, the equator is the same, right? But it is flipped, right? We need to change coordinates from the one that takes the South Pole to the North Pole. So we're going to just flip the South Pole and the North Pole in our suspension. That's that map there. And then comes the sort of difficult part of this construction, which is checking that this works. And this is given by this little diagram here, sort of expressed loosely. I'll go into it more on the next slide. But it relies on two important lemmas. One, I would say one important lemma, and then a number of little features about flip. So the idea, let's understand what we're trying to do here. Remember, we're trying to show that two functions here I'm defining them as functions, by the way. I shouldn't mention this. It's easier to define theta as a function and then inductively say that function is an equivalence because when you're checking that it's an equivalence, right? Being an equivalence is a proposition. You don't have to check any of this path stuff. So, and it's just a little bit easier to compute with functions than computing with equivalences, because equivalences remember the property that they're equivalents, and that gets transported around. Of course, it doesn't matter, but it shows up in your equation. So it's easier to just define it as a function that later is an equivalence, but just a little more verbose. So these are the functions that correspond to these equivalences written down here. So at the top, I have north. I wonder, is there a way on the normal zoom app, sorry, for me to like laser pointer over here? Does anyone know?
There
Oh,
should be.
never
In my head, there is.
You can use your cursor probably, yeah.
Oh,
It's
can
not
people
the
see my
best.
cursor?
You can see your cursor.
Okay, great. So this is what the image under north. This is the image under south, right? And then what family are we transporting in? We're transporting in families equivalences from the suspension of the tangent space to this fixed type here. So the transport in there was defined over here, right? The transport in T was defined over here. When we apply suspension to that, that just is the functoriality of suspension. So this is the suspension applied to this composite up here, and that's the transport here. So to show to give a target for this equatorial point P, or really the transport of this function on the meridian defined by this equatorial point P, is to give a filo to this square here. And so the most important lemma here, and I'll go into this in the next slide, is that flipping under, if you have double sigma, double suspension, flipping one component is homotopic to flipping the other. Now, once we've done that, the rest comes down to just naturality of flip, the fact that flip is idempotent, the fact that these are inverses, suspensions of functor, and this all just sort of collapses over here. So I'm leaving that sort of implicit. Okay. Are there any questions on this slide before I go over and talk more about these flippings and stuff? Right. So here are our three crucial lemmas about flip. Flips, the definition is given above, by the way. So one is it's natural. That should be pretty easy to believe. Second, and this is sort of in one way the most crucial one, is that if you have a double suspension, flipping on the outside is the same as flipping on the inside. It's not just the same, there's a very nice homotopy between them, I should say. And so I want to give a picture to this homotopy. I'm not going to define it for you, but I'll give a picture for you. And so let's put it, this works for any type A, in particular when A is the empty type. And by some sort of like, you know, if you will, polymorphism argument, it has to be determined by what it's going to do there. So when we put in the empty type there, we get a circle. And the flip of the inner flip or sigma flip here of the circle would be flipping over the y-axis. It's this one, flipping over the y-axis. That's this. Whereas the outer flip is flipping the second coordinate, is flipping over the x-axis. So it swaps the, you know, plus and minus y. Okay. And so these are obviously homotopic in a very nice way by rotating a quarter turn, right, counterclockwise. And there's something very, very special about rotating a quarter turn counterclockwise that sort of makes this tick ultimately. And I'll briefly mention this again. But basically, the circle is generated by rotating a quarter turn clockwise, counterclockwise, well, whichever way. And so this is a nice homotopy here. Okay. Finally, we have involution, which so when you look at the definition, it's pretty clear this is going to be involutive. And so these three lemmas were necessary to complete our definition of theta in the previous slide, but they also let us do something else really nice, which is compute what the antipode map does. So I've been talking about the antipode map for a while, but here's the definition of it. The antipode map flips every single coordinate in the sphere. So it's defined inductively by flipping and then suspending the previous antipode. So it flips every coordinate. Or I guess I went in the opposite order, it doesn't matter. So in particular, we can, by this lemma, and the fact that flip is involutive, and by functoriality of sigma, we can always replace sigma flip by another flip and then cancel it with an existing flip. So if we look out here at an expanded version of what the antipode, this is not a n times, by the way, this is the nth dimensional antipode. This has flip here like this, n plus 1 times, right? And what that means is that if n is odd, right, there's an even number of flips here, and they'll all cancel, and we'll get the identity. But if n is even, we'll have one left over, say this first one here. These will all cancel with each other, but we'll have one left over. And we'll end up with just one remaining flip. So this is nice. Even though the antipode flips every coordinate, it in fact is just either not flipping or flipping. Okay? And from this, we can prove the Hairy Ball theorem. So one, we can show, and this does take a little bit of work. We can show that theta p of north is equal to p. Well, that one doesn't take very much work at all, but we can show that theta p of north is equal to p as we defined it, and we can show importantly that theta p of south is equal to the antipode. So this is as we expect, and therefore we can get a map. So applying theta p, right, gives us a map from the suspension from the paths from north to south in the suspension to the image of north and south under theta p. But we just said that that was p and the antipode of p. So if we precompose by the meridian, we get a function that takes a tangent point and gives us a homotopy from the point p to its antipode. So in the picture, it's precisely this path. So remember that the tangent space is this orthogonal sphere, the equatorial point, the equatorial sphere, where the point P is the North Pole. If I pick a point on that sphere, I get a meridian, a relative meridian, going from P to negative P, or the antipode of P, sorry. And that's the homotopy that I get between them. Now, what this means is that if we have a section of the tangent bundle, in other words, if for every point we have a tangent direction, then we must have a homotopy between the identity and the antipode. So for every P, we have a homotopy from P to AP. And this is going to be a problem if our sphere is even, because if our sphere is even, remember that A is flip, and flip is not homotopic to the identity. And that is something that you can prove using cohomology or homotopy ending. So I'll go to that in a bit. So this is the sort of content of the Hairy Ball theorem, is you can't have a section of the tangent space on an even dimensional sphere. So this, by the way, I kind of love this. This is like very much the classical proof, and it's quite nice. Another thing I will say is that I think I'm making this look quite simple. The fact that these inductive arguments work is rather to me feels rather brittle, and if you make slightly different choices, it can be very hard to complete the induction. So, for example, if you try, and you might be able to do this where I wasn't able to do this, or but if you try to just define theta instead of as being this equivalence, as being this particular map, if you just try to define the induction on CP as a map between P and the antipode, then it becomes much harder to actually complete the induction. So even though it looks like it's like sort of the same argument, because after all, theta as a map out of suspension is effectively determined by what it does on the meridian, right? And the north and south. Once we know that, it turns out to be harder to complete the induction. So there's a subtlety involved in actually getting it all to work out. And I should note that this stuff is formalized. Dan has formalized this in a really nice self-contained file. This part with suspensions. Okay. That's Dan Christensen, by the way. That Dan. Okay. So B op plus. So now I'm going to talk a little bit about cohomology. So B op plus is going to be of X is the delooping of call the sort of positive or oriented automorphism group of X. And what this will be for us is pairs of a type Y and an element of the zero truncation of the type of equivalences of Y with X. Right. So in particular, the important one of these we need, well, we have two important uses for this, but one of them is if we plug in s to the n minus 1 or s to the n for x, then this becomes the type of oriented spheres. Because we have, so in particular, if you do have some kind of an element of this set of equivalences with the sphere, then in particular, you are merely a sphere, you're some kind of sphere. But you have this choice of a connected component of the automorphism group of a sphere, right? Which for which there are two, and those are that's your orientation. So this is why I've used a plus here in analogy to like GLN plus for the like positively oriented general linear group. So we can put orientations on our spheres. There's a sort of quick connectedness argument for that. Well, I don't think we've fully done this step, but we're looking into doing a really nice concrete one that builds up as we build up the tangent bundle as well. But in any case, it doesn't really matter which one you have it, you just need to have it. And I mean, they must be the same by connectivity arguments anyway. Well, not must, but okay. Once you've set the base point, they must. So we're going to define also the Euler class here to be this map that takes an oriented sphere and gives us an element of this b odd plus of kzn minus 1, which is the homotopy type with exactly one homotopy group, namely the integers in degree n minus 1. And this map is really simple because the n truncation of Sn minus 1 is our chosen representative of kzn minus 1, like which is a property sort of the type that uniquely determines it, right? So our function here is just going to be the function that takes an oriented sphere and n truncates it. And I've called this the Euler class because it is the universal Euler class. If you map into b op plus Sn minus 1 from any type, that is an oriented sphere bundle. And if you push forward by this, you get an element mapping into this other type, right? But thanks to the theory of banded types, which is done by Jarl Texeris and all my other co-authors, we have an equivalence here that proves that this funky type b up plus kzn minus 1 is in fact itself a kzn, in particular in a way that deloops this particular function that takes an automorphism of kzn minus 1 and evaluates it at the base point, right? So in particular, we have this that means that when you take the Euler class, it lands in integral cohomology. So it is the function that pushes forward an oriented sphere bundle to a class in integral cohomology. I'm going to open up my clock here so I don't spend too much time.
David, I'll just mention that it should be the n minus 1 truncation, just in case anyone was confused.
Oh, yeah, thank you. Thank you. Yes, it should be the same degree of truncation as the sphere. Yeah, this mistake might be propagated through some of the slides because the degree of the spheres I use kept changing. Because sometimes I'm in the inductive step and sometimes I forget to. Thank you. Okay, so we get this class in cohomology. Okay. So now let's actually compute what the Euler class of the tangent space is. And this time, now I've bumped up my degree by 1. This time it's correct. Okay, so here what we have is I've just written out at the top the composite E after T. That's the push forward of the sphere bundle T along E, or in other words, the pullback of E along T. So to calculate this, note that if we're in the inductive step here, so if we're considering our sphere as a suspension of a previous sphere, then we're mapping out of a suspension, and we can take the transpose under the suspension loops adjunction. So there's a little bit of fudging I'm doing here where really I should have that, it should go from loops to loops. Here I meant I go from n equals north equals south, or a path from north to south. So there's a little fudging up there, and then there's a little fudging a little bit below, and these fudges cancel each other out. So I'll just do it like this because it's a little easier to think about. Right? So when we transpose, we get this path along the top up here, right? Which goes from the sphere here all the way down to KZN. So this is our class in Z cohomology of the sphere. All right. So what is it? Well, we've transposed this, so we can precompose by the unit of the adjunction, which is roughly speaking the meridian. And roughly speaking, because you have to compose by the fixed path from north to south to turn this into loops, but whatever, again, we're going to cancel that out later on. And then we apply T star, we apply T, right? Because that's what it does on loops. And then here we apply E, but this was done by taking the n truncation. So applying the n truncation is just using the functoriality of the n truncation. That's what we have here. And then, as mentioned before, on loops, the map from B op plus KZN to KZN that considers this as the is delooped by the equivalence that shows that this thing is a KZN plus 1 is in fact evaluating at the point. So we can, by sort of the naturality of truncation, or the fact that this point is literally defined to be the image of north under truncation, we have this commuting square here. And this gives us, so this tells us that the Euler class is in fact the class of this map, or the degree of this map alpha here from the sphere to the sphere. And explicitly, this map is, you take the meridian, you apply T to it, you transport it over T, and then you evaluate at N. Well, we defined T by induction, so we actually know what it means to apply this to the meridian. We send P to this map, which takes Sn, considers it in the coordinate system where P is the North Pole, and then flips P with negative P, and then puts it back. So if we evaluate at that map at north, what that is doing is, in this picture over here, we take this coordinate system, right? We look at north, so somewhere over here, and then we move that, we flip it through the equator relative to P. So that's the map we're considering. And that map, its degree is the Euler class. And this is so far so classical. In fact, at this point, you have to just figure out how do you calculate the degree of that map. In the classical theory, you could use degree theory to do it. And so Dan has a calculation here in this file. It's really nice. That shows that if you apply alpha to the meridian, you're going to get this composite of the meridian of the antipode with the meridian at that point. Okay, and where that little caret symbol just means, again, fudge it so that you can actually compose these two things in the canonical way, the way that cancels out the other fudging I did. All right. So what's special about this is that if we know that a function on a sphere computes on the meridian as the composite of two meridional maps, that is precisely the structure of addition of classes, of homotopy classes of maps on spheres, given by using the co-group structure of the suspension. So that's the one that takes two copies of the suspension wedged together, takes a sphere with a meridian and then squishes it together into two spheres with wedged together at a point, using that co-group structure. So what this tells us over here is that, in fact, we have in the cohomology group, we have that the Euler class is the sum of the antipode and the identity. And now we can refer to the degree calculation of these two. A is either flip or identity, depending on whether the sphere is even or odd. So if the sphere is odd, then the Euler class is 0. And if the sphere is even, the Euler class is 2. So that's nice. So that's how we calculate the Euler class there. Okay, so as I mentioned, this story was done using suspensions. I wanted to present that because I think it's like, kind of really, really cute elementary, and it traces the classical story like really well. And that's one of the, so I'm sort of new to synthetic homotopy theory. One of the beautiful things I find is that it's really remarkable how well it sometimes traces the classical story, even though it's like so abstract, so bare. So it's really cool. So this is another case of sort of doing that as well, but it's a little more involved, and so that's why I went with the other story. But I wanted to describe this one because if we had to pick one, we'll probably go with this one. It's more general. It gives us also tangent spaces for RPNs, and it gives us a notion of sort of orthogonal subspace to a line, in a certain sense that I'm going to describe here. So here's the more general approach using joins. So a reflection is going to be an automorphism that satisfies the following two conditions. One of these conditions, which I'll call reflect here, says that if we go at the join of A with itself, A is some type, right? That if we reflect in the first component, that's homotopic to swapping the two components of the join. Okay. So in the classical world, where A was the real line and join meant direct sum, or in other words, if A is is S naught, the unit sphere of the real line. This is the two maps here can be expressed as matrices. The one where we reflect in the second component, or I guess this is the first component up there. But the one where we reflect has the -1 right here, right? And the one where we swap has the two basis elements flipped, right? And there is a homotopy there, given again by rotating counterclockwise by a quarter turn, right? So that's expressed here. And second, we have this coherence condition. And this coherence condition looks a little weird in homotopy type theory, but I want you to look at it from the point of view of what happens in sort of the ordinary classical world here, which is if I rotate this basis up to this basis, right? Then note that what happens, where does that element trace out my first basis element in left? So my first basis element here gets traced out like this. Well, that is the glue from it to itself when we describe it as the glue AA. That is the one that is that element there is the glue. So if you take a sort of principled look at what happens when you do it with S naught, you see that it makes this picture. So this is again a situation where we have this this is the same thing as the lemma in the previous one. It's obviously different, but it plays the same role, and it is very related. Okay, so next we have this sort of interesting definition here, and I'm wondering if anyone has seen anything like this. I apologize for the name. It's sort of just a name. But if anyone's seen something like this, I'd love to hear about it. So if we have a type with a reflection A, then we can consider an A orthorcer. And so what this is effectively going to be an axiomatization of the idea of being able to take orthogonal complements to A lines. And so how that works is this. We have a type family here, which I've called tau, which is the orthogonal complement. And then we have a theta here, which takes for any point on E, we get a joint decomposition of E through A with this epsilon. So if you think of one thing I'll note is that join works a lot, it is the homotopical version of direct sum in the linear world. And this is realized by if you take direct sum of two vector spaces and remove their 0 point, that's the same as taking, the two vector spaces, removing their 0 and joining the resulting spheres together. So that's how stable phenomena in bundle theory relates to stable phenomena in ordinary homotopy theory. And we're sort of using this analogy here. Okay. So another way to look at this is that these are the two pieces we were doing inductive definitions on. So the way to re-understand this tangent construction is as a join for these orthorcers. So if we take yep.
Oh, I've seen something like this before in literature about buildings.
Oh, wow. I'd love to hear about that. I'd love to hear about that. Would you mind staying after to tell me about it?
Yeah.
Fantastic. Sweet. Okay, so the join for orthorcers, we take the join of the underlying types, and then we define something that looks a lot like the tangent bundle construction we saw, the inductive step of the tangent bundle construction we saw, namely the tangent space or the orthogonal complement at a point in the join. It's again defined by induction. If it was in E, right, it's defined by, I think I have this actually. If it's in E, we take the orthogonal complement in E and join with F. And if we're in F, we take the orthogonal complement in F and join with E, and then we glue them together using both the thetas, right? So see, the tricky part of this is doing it with both the getting the glue on both the thetas, because it turns out to rely on a lemma that is 4 joins deep. It's just the lemma about the commutativity of join, and commutativity and associativity of join, which is coherent. So there is a filler there. We don't have it written down. So instead, we focus on just doing iterated joins of A considered as an orthorhomosphere over itself, where A is one-dimensional, so there's no orthogonal complement to a point. So it's just empty there, the constant family of empty, and therefore we get this the structure theta is constant at the canonical equivalence of joining with the empty thing. I wrote it as the identity there, but it's the canonical equivalence. And so we don't actually just have to take these powers of A. We can take A acting on a fixed orthorhomosphere and take powers of that operation if we think of that as a suspension for orthorhomosphères in the join sense of the suspension. And that's the reason that turns out to be easier to do is because you have this empty there. You end up a lot of the formulas are joining with empty. If you just take that out before you do the definition, you get an easier condition to fill. And that has been formalized as well. And we can also prove, I don't have it on the slide, but we can also prove that theta acts on the left component by scalar multiplication in a sort of evidently definable way when you're on the join powers of A. So this also produces the tangent bundles. So I think this is nice, and I would love to hear, Jonathan, where you heard this kind of thing before. But I'm going to go on because I have a little more to say. So before we end here, so I guess I should have said, are there any questions on this page before I go? All right, so there's a question. We have a sphere bundle. We've defined the sphere bundle. What makes it a tangent bundle? Like when is a sphere bundle a tangent bundle? And so I want to give a little first pass at an answer to this. This is not a complete answer for reasons I'll sort of dip into at the very end. But it's a fun enough answer that it gives us a way to define the tangent structure on the product of spaces. So I'm gonna go through that. And therefore we'll get tangent spaces on toruses and products of spheres. So the first idea is we have this sphere bundle, Tx, M is my base type here. Think of it as a manifold, right? And then one important feature about the tangent bundle is it should live sort of in the space very close to X. And in particular, you should be able to contract it back down to X. So that's one extra feature these bundles should have, right? You should have some map down, some other map. Note, it's not the projection. The projection just sends it all to X, which contracts onto the map X. Okay? But the other important feature is the rest. If you look at the sort of classical theory of manifolds in differential topology, you see that the complement of a point is used all the time. In fact, the notion of homology manifold it's a space of a suitable niceness where the relative homology of the manifold with respect to the complement of any point is that of a sphere. And so this is sort of the idea we have here is that the other important feature is that there's a complement bundle, which is some other bundle of homotopy types. Of course, point set theoretically, you could say that this is actually the point set complement, but we can't do that. Everything's homotopy invariant. So we have this other bundle, and they have to glue together. So if you note, the whole space M here is given by gluing together the point X with the complement through a bunch of paths marked out by the tangent sphere. And so that leads us to our definition of what I'll call here a homotopy pre-manifold. And I'll say why it's a pre-manifold in a bit. So a homotopy pre-manifold structure on a type consists of a push-out complement for every point of that type. So what is this push-out complement? Or it's not just any push-out complement, I should say, where the map at the back there is merely a sphere. Or another way to say this is a sphere bundle is in fact a tangent bundle in this sense, when you can complete this bottom path here to a push-out complement square. Okay. So this is very similar. If CPM, which is supposed to be the complement of M at P, were actually points at complement, this would be very, very similar to a definition of the tangent bundle of a topological manifold given by Lashoff 72. So in particular, remember that map CP, which mapped every point in the tangent sphere of a point to a homotopy between it and its antipode. That gives us a diagram at the bottom. And because effectively that map had just been pre-composing a equivalence by the meridional map, that it is a pushout square. It's sort of in a way the defining pushout square of a suspension. This map is the map which the fact that this isn't a pushout is because the co-gap map of this square is theta, right? This gives us the structure of a homotopy pre-manifold on the sphere. And I'll note that the complement is a point here because when you remove a point from the sphere, you get a disk, which is contractible. But where does it contract to? It contracts to the opposite point, the point at the antipode, right? Okay. All right, so suppose we have these homotopy. Oh, wait, I'll say a little bit about why this is a pre-manifold, not a manifold. One thing you'll note if you look at this is that we could always put a homotopy pre-manifold structure on any type in a dumb way by taking TPM to be the constant bundle at the sphere, n sphere, and taking CPM to be the wedge of the point of that sphere onto M at that point. Then the pushout would just sort of be contracting that sphere back down again. And this means that when you want to prove things about the intrinsic properties of M, given that it has a manifold structure, which you would want to if you're trying to import some of those differential topology theorems, this definition can't be enough. So I'll say some more about that at the very end, but that's why this is a pre-manifold structure. So suppose we have these two homotopy pre-manifolds, aka we have these two tangent bundles, right? How can we put a pre-manifold structure on the product into this? So how are we going to do this? Let's look at the one example I really know, which is the torus, right? So here's our torus, and there's a point PQ. That PQ lives on, has coordinates in the first sphere, which is green, and the second sphere, which is purple. So our generating sort of circles. Okay, great. So now what is the tangent sphere at that point going to be? Well, we can look at the tangent sphere is going to be a little circle around it, right? We know that. But which circle? Well, if we're at that point, we can go up and down on the green sphere. That's the tangent space it has at that point on the green sphere. And we can go left and right on the purple sphere. So that's the tangent sphere it has at that point on the purple sphere, right? And then note that those sort of those directions span the various directions we could go for anywhere at that point. So that's taking the join. So the tangent sphere at this point on the torus will be the join of these two tangent spheres of the constituent defined product spheres, the component spheres. Okay. So next, suppose we take the complement of the tangent sphere. So that's that little red disk there. Suppose we take the complement. What's left over? If you know the classical statement, you probably already know it's the wedge of two circles, right? And so which two circles, you might ask, and where are they wedged, right? Well, if we look at this picture, right, and I remove that patch in the front, right, there still is the antipode of both B and Q, those components there, that's drawn in orange. It's at the back end on the other side, right? So it's at the back end of the purple and it's on the other side of the orange. So it's on the inside of the donut at the back, okay? And I've drawn there two other circles. And those circles are what you get when you fix one of the components to be the antipode of one of the components and let the other ones vary, right? So if I fix the first component to be AP and let it vary, the rest vary, I get the other purple circle, this inner purple circle. And if I fix AQ and let the first component vary, I get this other green circle. And the point to note is that those circles, first of all, are still in the composite. in the complement. And secondly, and this is a little more difficult, they are the complement. if you can homotopy it, you can stretch it all back and around out, and then and put it back into just those. So this is the square we get here, and this is so this is the square we get here. Okay, so what can we learn from this? Well, the thing to learn from this is that despite the fact that this might look a little ad hoc at first, like I took a join over here, I took a wedge mapping down to the product over here, I actually did the same thing to both of these vertical maps. And what I did was I took the pushout product. So the pushout product is a product of two maps that produces another map. And what it does is it takes those two maps and it makes this square outside like here, right? Where in one case you do F and then you do G, and the other case you do G and then you do F. And it takes their pushout and uses the universal property of the pushout to get this map, this comparison map here. And that is the pushout product, right? Really it's the map, but I just named the domain the same thing, but it's the map, okay? And the important thing about the pushout product to note is that it generalizes a number of important constructions in homotopy theory. In particular, the pushout product of two terminal maps is the terminal map on the join. And the pushout product of two point inclusions is the inclusion of the wedge at those 2 points into the product. So this is what I did on the left-hand side of the, down here. This is what I did to the tangent spaces. I took the join, the terminal map on the join. And over here, the wedge, this is what I did on this map. So in general, we can say that if we have homotopy pre-manifolds M and N, then to take the to take the product structure, the product manifold structure, which lives on their product, we take the pushout product of the two defining squares. Pushout product is functorial, so that's how we get the horizontal maps down here. Now, this only works if we know that the pushout product of two pushout squares is a pushout, an important lemma. And so that's this following lemma. I don't actually, for reasons of time, although it turns out I had the time, for reasons of time, I didn't include the proof, even though it's just a really fun little diagram chase. It's one of those just really joyful little lemmas. But this is sort of the lemma that's important. If you have two squares, two pushout squares, and you take the pushout product vertically of them and use functoriality to get these horizontal maps, this resulting square is also a pushout. Okay? So I hadn't seen that before as well, and I think that that's it's fun to prove. The way to prove it is to do it sort of in a way one at a time, not trying to do them both at a time. So split this square up into a composite of pushout squares, and then look at each square one at a time. But I hadn't seen that before. So here's some future work. We're looking at comparing the Tom class of the tangent bundle to its Euler class. And we're looking at bumping up homotopy pre-manifolds to homotopy manifolds by describing a notion of stable normal bundle, and very importantly, the Atiyah duality you should have using the stable normal bundle stably. So that's what we will consider to be really the structure of a tangent space, is something that comes with this normal bundle that has the stable, that is the stable dual to the underlying space, which will imply all the usual homological features of the manifold. And that's all I have for you tonight. So thank you.
I forgot to mention we have traditional silent applause, but it seems like everybody knew the drill, so well done. Who wants to start with questions?
I've got questions.
Yeah.
Yeah, so once you said complement, it occurred to me that one way you might think about manifolds is you might try to define Spanier-Whitehead duality, which like you can't really because of Rn, but well, you can define it into Sn or something like that. And then the things that I might call manifolds are the ones whose Spanier-Whitehead duals are some desuspension. You know, when you take some tangent bundle, you get an appropriate desuspension. And so is this about what you guys have ended up doing? or can you define Spanier-Whitehead duality, or are you going based off of some just, you know, stable version
I
of
think
the
we were thinking stably, but let me see if I so we were thinking of the Spanier-Whitehead duality. That's how it got started, and then we figured it might just be better to just jump all the way to the stable version. But you're saying, so you say take do the Spanier-Whitehead duality, and then you want the dual to be a desuspension.
Well, so I mean, I think it's probably what you guys ended up with, but the nice thing about a Tia duality is the dual of the manifold is, you know, m to the minus tm.
Yeah.
So it's the fact that the Spanier-Whitehead dual of the manifold is somehow capturing some bit of whatever the tangent bundle is. It's capturing the, you know, the Tom space.
Right.
So that's the only observation, is that like somehow the tangent bundle turns up when you try to do Spanier-Whitehead duality.
Yes.
Which
yes.
a priori seems sort of unrelated, or maybe you could phrase it in an unrelated way, but it's tied up with duality theory.
I will say that, so if you look at this definition and you take the sort of obvious maps to Rn. So first of all, what is Rn? I didn't say it here, but Rn is of course the point with a tangent bundle structure, which is namely the Sn. So I think that's fun. Sn and the identity, and then, you know, the fact that the pushout of the identity is what gives you that this is a pushout square here. So you actually get all your different Rn's. And if you, a map of these is really some kind of embedding of manifolds, weirdly enough, because the reason it's an embedding is because it maps complements to complements. And then so if you suppose that you can embed in Rn, then you or it's not really an embedding, it's sort of some kind of inclusion. And an embedding is when you can have a joined complement of the image of the tangent bundle. So like, you know, you have a map from, you have some other thing and you join it with it. And that would be the normal bundle of your embedding. And when what we've been starting with is some data that's like that and moving it around. I wonder if that's, and like that, the idea is to take a map like that and then try to turn that into something that has a property, and then which corresponds to the duality prop, the fact that it exhibits a dual, and then that would be a property. Just like I wonder if that's anyway. I would love to. I think we're still really playing on that stuff. It is future work. We really are playing around with it. So
Cool.
yeah, I'm not sure if you might have just you might be just able to give us a new idea here. So I'd like to chat further if you're up for it. I don't know. Yeah,
Absolutely.
And now can I ask you a question?
Sure.
Which is, you said that you've seen this notion of orthorser before in building theory.
So it's maybe not quite this, but what you end up with is, so when you look at, so what's a building? Let's say what my definition of a building is I have some vector space, and I look at the category without the top and bottom elements of all the subspaces of that vector space, and then I take the nerve of that category and I geometrically realize it. So that's like a very classical description, and that thing is called the building, and it ends up having being a wedge of spheres, which is weird. It's a beautiful classical fact. It's just a big wedge of spheres. But then it turns out if you want to talk about like decompositions of these things, you end up having to do exactly constructions like this. So you might think that, like, let's say, well, if I have one vector space and another vector space, then their join, it turns out like their join sort of embeds into like the join of the buildings embeds into the building of the sums of the vector spaces, but it's not the whole thing. But they're sort of constructions where you can sort of complement appropriately, then parameterize on some like complement, and as you parameterize over this as you move over the different vector spaces you're parameterizing or you're complementing by, you end up getting this parameterized join of buildings.
Oh, awesome.
And it looks just exactly like
awesome.
this. And it's
That's great.
yeah.
Yeah. So one of the ways we got into this was we were trying to do trying to get at the Grassmannians, which sort of require this in a way sort of seem to require iterating this kind of idea here. So I wonder if some of these if we can poach some ideas from the theory of buildings, the homotopy theory of buildings, to get at these kind of orthogonal structures.
That's a very fun idea. Yeah.
Thank you. Yeah.
Yeah.
Very quick question. Thanks for your talk. I was going to ask if this gives any insights into the construction of Grassmannians. So it sounds like that was at least the motivation for the beginning. I wonder if you feel any closer to realizing that.
I don't think we really feel any closer. I mean, I personally don't feel that much closer. The idea, sort of naively, is just that, like, if you can show that this join of orthorhomers works hereditarily, so that you can, if you have hereditary sort of like n-1 dimensional orthorhomers structures on these things, then you can join those together. Then you could get, we have a fun name for a thing we haven't been able to construct. It's an armillary sphere. The idea being like the tangent sphere bundle on the sphere, but also on every tangent sphere, its tangent sphere, and so on and so on. And then whoa. Is everything normal on your end? You're okay?
Yeah.
Okay, well, something changed in my screen. It's really dark now. It's okay. Yeah, so right, that's right. We tried and we haven't quite gotten there, but yeah.
Sure.
But maybe we should try again. I mean, we've been running in the way in this homotopy manifold direction as well. So
I mean, they're yeah, elusive for sure. Yeah.
I was wondering, you said that you use the join representation of spheres instead of the suspension one. I wonder if it's for the sake of generalization or because of the technical benefits. I would expect the lemma about the flip, for example, that it doesn't depend on the coordinate, to be much more doable with the join view of the sphere. Is my guess right?
yeah, there is a technical benefit in that you sort of have to double work with the suspension because you have north and south. On the other hand, you have fewer point generators, which can make it look. I would say the join one looks a little odder personally. That's all I would say. That's why I decided to present the suspension one here. However, it is more general, and it is in many ways it's a bit smoother, and it's actually the one we came up with first. So so we sort of looked at it and then turned it around into the suspension one rather than the other way around. I don't know if that answers your question here. We also get the real projective spaces, the tangent, which is of course not very different than the tangent structure of the sphere, but it's like, the fact that it descends is something that's kind of difficult to do. I think with the suspension one, at least, it's not very obvious. But with this one, because we have this extra variability of our types, we can do it sort of over, B aught S naught, and pull out of that the sort of C2 equivariance of the structure on RPN, of the tangent structure on RPN as it relates to the tangent bundle in the sphere. So the fact that it's the same thing under the quotient is sort of pulled out just by type dependency, which of course is easier than trying to do it as a map. Dan, did you want to say something about this point? I think.
Well, yeah, I could maybe just elaborate a little bit that, I think the main reason is the generality, as David said. That's the reason we like the join one. In particular, you can start with a particular A orthotorsor, and then iterate joining it, and we get new things. In terms of formalizing, there's pluses and minuses. So there's certain things where you can do half as much work from the join point of view, because you like, as David said, you unify treating the North Pole and the South Pole. They're just two different elements of the two element type that you're using. But there's other parts where it becomes technically quite a bit more complicated. So it's a trade-off in terms of formalization. I wouldn't say, well, I would say the one with suspensions is a bit easier overall, but like I said, it's the generality we're hoping for. So we're focusing on the approach using joins. But I formalized both, just partly because I got stuck on one and tried the other, and then went back and forth, and I got them both formalized.
Thank you.
I'm sorry, is this formalization in the Coq repo, or where is it going to be?
So it's using the HoTT library, but it's currently not public. It's
Okay.
Still being cleaned up. So I've been
Sure.
gradually pushing background material to the HoTT library about joins, for example. We needed to have the proof of associativity of join and other properties like that. So that's been pushed. But there's a lot more background work to still push before the main results can be moved over there. But they will be.
Cool. Very cool.
Jonathan, we could talk about about a duality again, if you would spin your whitehead duality.
Sure.
I don't have anything more to say. I felt like I cut you off a little bit earlier.
Oh, no, you didn't, and I'm happy to take this offline or do it after the seminar as well. No, I mean, I was just saying that, like, for all theorems, like, I mean, most of the things that I like about manifolds are captured by Spanier-Whitehead duality. So in particular, I spend some percentage of my life thinking about, like, Lefschetz theorems.
Mhm.
And you can basically extract those from Spanier-Whitehead duality.
Mhm.
I'm like, that's sort of like enough. And if you have some reasonable notion of joins, which you do for types, and maps into spheres, which you do, and some way of stating that you have duality, maybe stably, then that buys you quite a bit.
Yeah, that's exactly what we were hoping for, as a definition of a homotopy manifold.
Okay.
So sort of one of these things where that tangent bundle is involved with this normal bundle, and they together exhibit Spanier-Whitehead duality or HoTT duality.
Yep. Well, that's really cool. Yeah. So then you could even hope to get some kind of Lefschetz theorem, because it's in some sense like it shouldn't be so much harder than, I don't know, a Hairy Ball theorem, because it is these one of these index theorems where you basically, I mean, there's got to be a different way to say this, but you have to remove, like, you pluck out the fixed points and then get a bunch of self maps of spheres and sum those up, and then there's sort of no other homological data on the rest of the manifold.
One of our problems is this plucking out thing.
Yeah,
very,
yeah,
very
I would
difficult.
assume.
And I would really love, like, one of in fact, the real problem with this definition of the pre-manifold is just that the complement can be anything. Like, if it was the point set complement, this would be a perfectly good definition that you could finagle, I think, you could probably finagle it into a duality statement. I think you can, actually, because I think it is it's implied in particular by this. It's essentially the same thing as this one for topological manifold. So it does essentially, if CPM was actually the complement, this is effectively saying you have the homotopy type. This is rough. This is not entirely true. You know, there's a nicer point set definition in there, but it's effectively the same thing as saying you have the homotopy type of the topological manifold. So like you should, in other words, you should be able to get all that stuff. But the complement, this thing is just completely unstructured. It's like, you know, this map here is just something, right?
Yeah.
And that sort of is, and in general, this idea that I think we were thinking about like, oh, can you like, if you have a point in here, could you complement that too? Which is important for, as you're saying, you have to puncture out not just one point, but like multiple points when you do this. And there's something weirdly, a moment's coming to believe that manifolds are really about like punching holes into spaces.
But that's how all the proof. I mean, that's how you do every proof involving a manifold. Basically, you
Right.
puncture it somewhere, and you know what the puncture looks like.
Right. Right.
Yeah, so we'd like to know that the complement is a manifold as well.
Yeah.
But we can't just say that that's the definition, because it's recursive in a way that doesn't ever end.
Yeah.
So we toyed around with saying that for any finite set of points, you have to specify the complement or other things like that. But it's really hard to pin down what axioms you should put on a structure like that.
Yeah.
It's maybe worth pointing out too that even just this weak definition, because this is a pushout square, the cofibers of the vertical maps are equivalent. So you get that
Yes.
the cofiber of the right-hand map is an n+1 sphere.
Mm-hmm.
So that
So
tells you
this-
that the manifold has the right local homology at every point.
Right. I probably should have said this. This implies that you're a homology manifold if this were actually the complement.
Right.
of
Yeah.
the
Yeah.
one. Yeah. Which is where the name sort of comes from in a way.
Yeah. It's producing the complements. It's like if I said that I just had some sort of duality in hand, like can make a lot of this stuff go. But yeah, actually having a complement's a pain. Anyhow, I'd love to talk about this more later. As I said, I think a lot about Lefschetz
Yeah.
things categorically.
Sweet.
Okay, if there are no further questions, maybe this is a good time to take it offline. So thank you, David, and let's do one more round of our silent applause. Great. And finally, for the benefit of the YouTube audience and the live audience, so this is the end of the HoTT semester for the fall 2023, but we will be resuming in 2024 on February 1st. Stay tuned for the announcement.